Okay, here we go. So we resume, and where were we? We want to first we want to see okay, we have to establish this subjectivity. Okay, but first we want to note that if I look at this covariant and the functor of assigning extended graphs to graphs, okay, that obviously it preserves the injectivity of graph homomorphisms. That's what we already discussed at length. So if we start from an inclusion is injection, I extend it, okay, I have an extended graph, so this will also be an injection. And in fact, it will be an inclusion because you can very easily convince yourself that the extension of f intersects g is just the intersection of the extension of f with the extension of g. So this is just f extended f intersected with extended g. Okay, so it's obviously again an inclusion. And because inclusions are of course proper graph homomorphisms, okay, we know by this lemma 2.27, which says that whenever I have a proper graph homomorphism of graphs, then the induced map exists and is a homomorphism between path algebras. Okay, so now we have these homomorphism of path algebras 220. And it's obvious that if I prove that the 220 homomorphisms are surjective, I immediately get the 219 is surjective, right? That's completely clear because the homomorphism 219 are just quotient homomorphism of the homomorphism 220, respectively. Okay, so obviously, that if 220 is surjective, then the induced the quotient maps are also surjective. So how do we prove that they are surjective? Well, there was an exercise which I believe Majid was doing, a very simple one, but let me very quickly go through it. It's always good to remember it. That when I take this functor of finitely supported maps, okay, and then I claim that the injection is turned into the surjection. So if I have an injection from x to y, then the pullback map from finitely supported maps on y into finitely supported maps on x, and I don't care about the algebra structure. I'm looking at it as vector spaces or abelian groups, whatever. Okay, but this map is surjective, and indeed, if you take any finitely supported map from x to k, then you can construct the following map beta. You take any element y in y, and if it is in the image of f, then there exists an x such that f of x is equal to y. But because f is injective, this x is unique. So I can extract it from this equation and you can apply alpha to this x. And if y is not in the image of x, you just assign 0 to such a y. And obviously it defines a finitely supported map, because if it is finitely supported on one piece and 0 on the other piece, then it is finitely supported global. Okay. So beta is an element of finitely supported maps from y to k. And now clearly, if I apply the pullback of f to beta, then I get alpha. Why? Well, take any element x in x. F star beta of x is by definition, I should have put 2 dots here. This is by definition beta of f of x, but beta of f of x by the construction of beta is nothing but alpha of x. So we are home. Okay. So now to conclude the surjectivity of the homomorphism 220, it suffices to observe that the injectivity of graph homomorphism implies the injectivity of the induced map. All right, and I hope it's clear. Well, when I look at paths FPE and in FPE and paths in FPF, well, these are finite paths. And remember, because this is a graph homomorphism, we are talking about the induced maps that preserve the length of the path. So in other words, it preserves the natural grading by length of the space of paths. And clearly we are good at grade 0 because this is just mapping vertices to vertices. We are good at grade 1 because it's mapping edges to edges. Here by assumption, we are injective. And now if you take paths which are longer and we write the equality f of p is equal to f of q, well, then because it's a graph homomorphism of paths, when we write p as a concatenation of edges, and we write Q as concatenation of edges, we will have something like f of E1 dot 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 f of En must be equal to f of E1 prime dot 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 f of En prime. Of course, because f preserves lengths, the length of P must be the same as the length of Q. So I'm using different edges, but the length must be the same. Well, and now when you have such an equality of paths, well, you know that the edges and these guys are also edges, not some other paths. This reasoning doesn't work when f of an edge is not an edge. But if f on an edge is always an edge, then I have that f of E1 is equal to f of E1 prime, f of E2 is equal to f of E2 prime, and so on and so forth. But then I know I'm injective on edges. I conclude that EI is equal to EI prime. So this means P is equal to Q. So we are injective on paths. Okay. So this means that our assumption that this map is injective is satisfied. So when I apply this contravariant functor or find the supported maps on the space, then I'll get a surjection. Okay. And now I have the surjection here, which implies that I have surjection of Levi-Pavlovich. And now I'm going to turn from this, high school mathematics to something a little bit more fancy. And now I'm going to support myself by a beautiful result from the book. Sorry, let me erase this smudge. But first, observe the following. That now to make sense, I have to explain to you what I mean by gradings. Okay, and this means that I have to go back quite substantially in the lecture notes. I have to go to the place where grading for Levi-Pavlovich algebras is defined. And I suppose it's right after the definition of Levi-Pavlovich algebras. It should be around the page 40 or something. Yeah, unfortunately, I cannot scroll it any faster. I see that this drawboard PDF is designed really for slides. When you have 20 slides, it's easy to maneuver. When you have 80 pages of text, it's a little bit more subtle. Okay, that's path algebras, but I'm going back to the very definition. And there I should have this definition of the grading. Okay, path algebras. That's the very definition. And here we should have some elementary facts. Well, but I don't have what I want. Where's grading? What if I search for graded? Searching the PDF. Okay. Yes, page 52. Okay. So that's faster than scrolling. Okay, so first, there's a general definition of what one means by a graded algebra. Yeah, so for any monoid gamma and any algebra A, we say that A is gamma graded if only we have this direct sum decomposition of A into homogeneous components A gamma that satisfy the crucial property that A gamma times A gamma prime. Sorry, there is a typo. This, oh yeah, I have this. This is not A prime. This is A gamma prime. Okay, so there's no prime over A. There is a prime next to gamma. So A gamma prime must be contained inside A gamma prime. By the way, I cannot resist mentioning that you say that your grading is strong if this inclusion is the equality. And this is a very important condition because it corresponds to free action. You see, if gamma is an abelian group, okay, then strong grading by an abelian group is the same as free action on an algebra by its Pontryagin dual. So that's a very neat fact. But okay, that's not what we need. We are just saying, all right, but now obviously KE is n graded, so it's graded by the monoid natural numbers by the length of paths. Okay, and that's the grading we adopt. And now I want to go to relative con. Well, actually, maybe I can again search graded, and it will be faster. Right. Maybe it will be faster than scrolling. Now to tell you how it goes for relative conpath algebras. Well, you can very easily, okay, let's go to 63. Yes, that's exactly what I need. So you see, searching is, after all, faster than scrolling. Okay, so I'm interested in points 4 and 5. Okay, so when I take the extended graph, I can set the length of an unstarred edge as 1 and the length of the starred edge as -1. And then I obtain a natural Z grading of the extended graph, of a path algebra of extended graph. Okay, so I take any path, and I compute its length by counting all non-starred edges with weight 1 and counting all non-starred edges with weight -1. So in other words, I subtract the number of non-starred edges from the number of non-starred edges. I subtract the number of starred edges. I compute the difference, and this is the length of my path. And of course, this gives me a natural Z grading on the path algebra of extended graph. Okay. But now, if you look at the defining ideals, the defining ideal of a relative con path algebra, then you see that these are elements of grade 0. Let me scroll up to show you. See, these are the defining elements. And all of them are of grade 0, okay? Because this is of grade -1, this is of grade 1, so when you multiply, it's of grade 0. This is a projection, so it's a path of length or idempotent, so it's a path of length 0. Again, grade 0. And much in the same way in this part too. And because you generate your ideal by things of grade 0, this means that the generated ideal is also graded. And there's some general algebraic reasoning that says that if you divide, you see, this is crucial. You see, by multiplying by elements here does not change the grade of homogeneous component. That's why it works. Okay, so that's why the ideal generated by these sets 1 and 2 is again a graded ideal. And there is some general reasoning that says that if you divide a graded algebra by a graded ideal, then the quotient will be again natural graded. So roughly speaking, it looks like that. You have your algebra is graded. Your ideal is graded. And basically, you can think about I gamma as the intersection of I and A gamma. So A gamma and I. Okay. And then it's crucial that this holds again. And now when you compute the quotient A mod I, it turns out to be again graded by the quotient A gamma divided by I gamma. So if you divide a graded algebra by a graded ideal, the result is again a graded algebra. And this is the induced natural grading. Okay. So that's, we take this Z grading on the Levitt path algebra extended graph. We note that the ideal that gives us the relative conpath algebra is also graded by Z. And we conclude that therefore, we have the induced Z grading on the relative conpath algebra. So in particular, we have the induced Z grading on the Levitt path algebra. Okay, so that's what we want. Now let us go back to the beginning. Again, Can I scroll it any faster? We're almost there. Yes. Okay, so observe is here that because here we are talking about graph homomorphisms, the induced maps between the spaces of paths preserve the length. And if they preserve the length, they preserve the grading of the Levitt-Pav of a Pav algebra of extended graph. Okay, and consequently, when you go to the quotient, the induced map will also preserve the grading. So I can conclude, right, that now when I look at this surjection, I have a surjection from LKF onto LKF intersect G, and I have a surjection from LKG onto LKF intersect G, right? So of course it's the same as LK is. So the Levitt-Pav algebra of intersection graph must be just the quotient of the Levitt-Pav algebra of F by an appropriate ideal, and likewise on the other side. But now, because this is a graded homomorphism of algebras, because it is induced by the map which preserves the length of paths in this Z sense, okay, with negative lengths admissible, I conclude that the kernel, which is respectively IF and IG, that these kernels must be again graded ideals. Okay. So consequently, their kernels are graded ideals, and when I quotient these Levitt-Pav algebras by these graded ideals, I obtain an isomorphism of graded algebras. Okay. And now this simple observation, which we concluded from studying, surjectivity between Levitt-Pav algebras and noting that we preserve a length of paths. So the simple observation 221. Now we want to connect with a very beautiful and deep theorem, which basically you can find, although it's a little bit undercover. It took me a lot of browsing and putting together things so that I could conclude this theorem. It's not like you can find it directly in the book, but it definitely is just obtained by piecing together some fragments from the book. You have this extremely powerful and beautiful theorem, which says the following. Let E be any graph and K be any field. Then the quotient of the Levitt-Pav algebra LKE by a graded ideal, so that's precisely the situation we are in above, okay, is isomorphic, is graded isomorphic to the Levitt-Pav algebra of some subgraph E prime, where E prime is an admissible subgraph of E. Okay, so this is a very, very powerful theorem, because it tells you that when you look at the quotient, well, this quotient is again the Levitt-Pav algebra, and is the Levitt-Pav algebra of an admissible subgraph. So I'm not saying that it's an exact implication, or we have an isomorphism, right? We might have a subgraph in F which is isomorphic to the intersection, okay? But nothing should prevent us from saying, all right, so if you want to be home and dry, since we are in exactly the situation 221, basically for this 221 to work, we should assume that the intersection F intersect G is admissible in F, and F intersect G is also admissible in G, right? And better still, we have another very, very important structural result, which tells you what is the kernel of this map. But I will need it later on. So let me skip it for the time being and come back to it when we need it. Okay. For the time being, I need only this first part of the theorem. And so connecting 221 with this theorem 254 from the book, we infer that the intersecting of F and G should be admissible to ensure the existence of homomorphisms 219. See, these homomorphisms 219. We want them. And somehow to ensure that they exist, okay, we better have this intersecting of F and G admissible. And now here we have a certain funny logical property. I remember there was a debate about it in the first semester. Why do I say that the intersecting of F and G should be admissible instead of saying that the intersection of F and G should be admissible? Well, because I say by definition, and it is in the lecture notes, that the intersecting of F and G is admissible if and only if the intersection graph is an admissible subgraph both in F and in G. So you see, this definition depends not on what your intersection is, but what actually intersects. So I might easily find two different graphs which will have the same intersection as graphs F and G, okay? So the intersection alone tells you nothing. You have to say what you're intersecting with what. Then you can make sense out of this admissibility property, okay? All right, so now you see somehow by saying that we are in this setup of 219, step by step, we concluded that actually this admissibility is forced on us. That it's hard to see how we can go around because of this big theorem 254 from the book, okay? But also the other way around. I mean, let's assume that our inclusion is admissible, right? And now we would like to conclude that the induced map exists, but we know what are sufficient conditions for this induced map to exist, right? So we want to check properness, target bijectivity, and CR condition. And I claim that all of them hold. And this is a very nice reasoning, actually. Okay. So for starters, any admissible inclusion is proper because it's an inclusion, right? Any injective map is proper. Now, it satisfies the target bijectivity. Why? Because if you take the second admissibility condition, maybe instead of scrolling, which will take forever, I will just, yeah, let me, I'm wondering if I should start sharing a Blackboard to have enough room. Maybe so, yes, maybe so. So let me now share. Okay. Whiteboard. So what is admissibility? I say that E prime in E is admissible whenever the following two conditions hold. So for starters, when I subtract from the set of vertices in E, the set of vertices in E prime, but it must be hereditary and saturated. Well, for those of you who are with me from the very beginning, like Niklas, they know it by heart. But these are very simple definitions. So let me remind you of what we mean. When is a subset? So that's in full generality. When is a subset in the set of vertices? So let's take some graph F. Take the set of all vertices in F, so F0. When is such a subset hereditary? Well, basically the condition tells you that if you start any edge, so this is your H, this is your F0, it tells you that if you start any edge in H, and this edge ends somewhere, then the end of this edge must also be in H. So in other words, your subset is hereditary if you cannot walk out of it. Okay, so anywhere you walk, you are still in H. You cannot walk out of this set. So this is hereditary. And saturated is a little bit more fancy because it requires the concept of a regular vertex, but now we know very well what regular means. Okay, so this is hereditary. Saturated means the following. Again, I have my subset H in my ambient set F0. So, well, you know, it's like with the definition of when a set is connected. A set is connected in topology when it is not disconnected. And then you say, what do you mean by disconnected? So here it's the same thing. I say that my set is not saturated if there exists, if my subset H is not saturated, if there exists a regular vertex V outside of H, which maps all its edges into H. But V must be regular. Of course, regular enough. Okay, so this is what we don't want. If you have infinitely many, no problem. If you have a situation where you have finitely many mapping to H and say finitely many mapping outside of H, is also fine. The only thing which we do not allow is that you all finitely many edges are mapped into H from outside of H. That's not allowed. Such a vertex V is called a desaturating vertex. So you can say that your set is saturated if there are no desaturating vertices. Okay. So that's condition number one. Now condition number two concerns the edges. And it is the following. It says that if you look at all edges in prime, I'm sorry, it's hard to distinguish my prime from my one. In LaTeX it's much simpler. But it's simply taking all vertices in E prime and then taking the preimage but under E, the target of E. Of course, so if instead of TE I would put T prime, it would be nothing, right? It's obvious that if I take any well, actually, yes, of course. It's obvious that when I take the preimage of the whole of the set of all vertices in my graph under the target or source map, I will get all edges, right? That's obvious. But now because I put here TE, so this is the target map of the ambient graph, then I'm basically telling you is that if I have any edge in my ambient graph which ends at the vertex, which is in the subgraph, then this edge is also in the subgraph. Okay, so that's the second admissibility condition. And now I'm trying to tell you that if we combine this injectivity with no, sorry, what I want to say is that if I'm admissible, yes, if I'm admissible that an injective, sorry, I'm injective. I'm admissible, then I obviously satisfy the target bijectivity condition. Why? Okay, let's see. And now let's recall this target bijectivity condition. Well, I have the condition that for any edge X, so now the map F, oh, I'm sorry, I'm switching between E prime and E and F, sorry, I'm not so consistent. I have a map F, lowercase f from E to F, and I take X, which is an edge in F. I'm saying that if I take the preimage under X, under F of X, and I take any edge here, then mapping it by the target map in E, the endpoint, and of course this element is in the preimage of the endpoint in F of my edge X. that this is bijective for index. But now look what it means when f is injective. When f is injective, it basically means that this set that you are talking about here on the left is either empty or one element. Okay, so if x is not in the image of f, if it's not in the subgraph, then this pre-image is empty. But let's maybe consider the other side. Okay, let's look here. Again, here's the similar situation, right? So either this x ends at a vertex which is in a subgraph, or it doesn't. If this edge belongs to E0, so it ends in the subgraph, okay, then of course this pre-image is non-empty, so it must be one element, right? Because it's an injection. So this set is either empty or one element set. But now by this edge condition of admissibility, we know that if x ends in a subgraph, then x belongs to the subgraph. So this means that this is also a one element set. Simply is equal to x. Remember, this is just an inclusion. Okay. Now, otherwise, if this x does not end in E0, does not end in the subgraph, then of course this set is empty. The f inverse of tf of x is empty. But of course, x cannot belong to E1, because if it belonged to E1, then its end would have to be in E0, which is assumed not to be. So x does not belong to E1. So this set is also empty. So this means that this map is either a map between two empty sets, or it's a map between two one element sets, and that must be bijection. So you see how combining this admissibility, how admissibility gives you this target bijectivity. Okay, so that's one argument. Now I have to go to sharing again the screen. Yes. So we just went through the target bijectivity is satisfied by the second condition of admissibility combined with injectivity. That's exactly what we just did. Okay. And now the final one is that it enjoys the CR condition by combining, again, of course, the injectivity with the saturation and the second condition of admissibility. Okay, and let me again go to the whiteboard to explain why. As Fermat would put it, the margin is too small to write the proof, so I'm using the white. Okay, so now I want to prove a CR condition. What is the CR condition? It means that irregular vertices are mapped into irregular vertices. So in other words, I have that f of E0 less regulars in E is contained in F0 less regulars in F. Okay, so in other words, what must not happen is that I have a vertex which is not regular and it's mapped to a vertex which is regular. But this mapping, just remember, is an inclusion. Okay, so I look at this vertex in my subgraph E, and it is not regular, and it must not become irregular when looked upon at the ambient graph F. But you see, what does it mean not to be regular? You have two options. Either it's a sink or an infinite emitter. Well, if it's an infinite emitter, you are done, because if you're an infinite emitter in a subgraph, of course you're an infinite emitter in the graph. You might at worst add some edges, but you cannot take them out. All right. So the only other possibility is that this vertex is a thing. Okay. And indeed, you might think, all right, so it might become regular if there are some finitely many edges that start here. Right, but then these are finitely many edges that are in this graph F, in the ambient graph F. Okay, and remember, what is the saturation property? We are saying that the set F0 less E0 is saturated. Well, but this means that there does not exist a desaturating vertex outside of here. But what is outside of here? That's just E0. Okay. And then remember, this is in my E0. So I'm saying that there cannot exist a vertex in E0 which has the property that is regular in F and maps all its edges outside of E0. That's exactly not allowed, but this is exactly what would happen here. Okay, you might also say, well, there is a certain gap. How do I know that these edges are mapped outside of E0? Okay, so assume for a while that you have the situation that you have this vertex V in E0, because being in E0 is being outside of F0 minus E0. And well, whatever you say, it must emit an edge, but it didn't emit any edges in E. So if it emits any edges, they're only in F. So if you have an edge which is completely in F, and it starts and begins at E0, well, you have a contradiction with this second admissibility condition, because if you have an edge which ends inside E0, okay, then it must belong to E1. Wait a second. Do I do? Yes, exactly. Yes, exactly. Yes, that's the property that you have of for these subgraphs. Okay, so this inclusion is admissible if you have this property that any edge which ends in the subgraph belongs to the subgraph. So if these edges weren't going outside of E0, they would end inside E0, and then by the second admissibility condition, they would be edges in E. But that's not allowed because we assumed that in E this vertex is the same. So here I have a contradiction. So you must have all edges going outside. Okay, and when you have all edges going outside, but it exactly violates the saturation property of F0 minus E0. So I find it as a very cute reasoning that shows you that indeed, by using appropriately the admissibility condition of the inclusion E in F, you can prove that indeed the CR condition is satisfied. So that's very good, right? It would be very disturbing if we're contradictory, because we basically know, I mean, it's not like an if and only if theorem, but it's hard to think about a more general category of graphs and graph homomorphisms that would induce contravariantly a homomorphism between Leavitt-Pav algebras. I'm pretty certain that is more or less optimal. Okay, I don't have like no-go theorem or if and only that if it induces a map then it must be of that sort. No, but basically I cannot imagine how to do the proofs that the induced maps exist without these properties that are spelled out in the definition of this funny category CRTBPOG. Okay, so that's okay. You know that you shouldn't restrict it, and then we realize that all right, if we want to combine it with other assumptions, well, we basically restrict it to things that force on us injections, and so we just consider subgraphs, And then by this reasoning with the help of a big theorem from a book, we decided, all right, so basically we have to talk about admissible subgraphs. So of course, it's good to check it the other way around. What if we're admissible? Does admissibility guarantee that it induces a map of Levitt-Pav algebras? Yes, it does, because we very easily verified the conditions, and now this the TB and C are condition, and properness is obvious because we are injective. So now by our contravariant functionality theorem for Levitt-Pav algebras, we conclude yes, that whenever we have admissible inclusion of graphs, then the induced map in the opposite direction with Levitt-Pav algebras exists. Okay, and we also proved, by the way, that it is surjective. Right. So now let me go back to sharing my screen. Okay, why can't I scroll? Okay, I can. So you see, now one might naively think that combining the admissibility with one color condition of corollary 2.53 yields a push-out to pullback theorem for Levitt-Pav algebras. Why? Because you see, already we argued for admissibility, why we should have it. And if you look at these assumptions that you have for the Levitt-Pav algebras of extended graphs, well, then of course you have 1 and 2, and you have the push-out diagram in the category of proper graph homomorphism. So the 0th assumption first and the third are satisfied. So the only thing which is an additional assumption is this specific one color condition. Okay, so one might think, all right, if I now combine it with one color and admissibility, perhaps I should get a push-out to pullback theorem. Well, perhaps you will, but the thing is that this turns out to be too strong. I will show you an example where this one color condition fails, yet by all means we do have a push out of graphs which yields a pullback of the induced Levitt-Pav algebras. Okay, so that's too strong. The one color condition of corollary 2.53, I have to say of which corollary, because these one color conditions differ between the corollary 253 and the theorem to whatever. So that's too strong. But on the other hand, you can convince yourself that admissibility alone, although it is sufficient to induce a surjection, a canonical surjection at the level of Levitt-Pav algebras, the admissibility alone is too weak to prove a pullback theorem. I'm not sure I can offhand cook up a counterexample, but I'm certain that it's related to breaking vertices. That's for graphs without infinite emitters, there is no problem. This would be enough. Admissibility is enough. But if you have breaking vertices, then the situation is a bit more complicated. And without some additional assumptions, this push-out to pullback theorem is simply false. So admissibility alone is, in full generality, a little bit too weak. Okay. So what I want to argue for, and this is, the crown jewel of 3 semesters of teaching, that's exactly what we are talking about. This is this take-home message, take-home theorem, which is a new result. And it says the following. So let F and G be arbitrary graphs and K be any field. Now assume that the intersecting of F and G is strongly admissible. I will explain in a second what I mean by strongly admissible. It's admissible, and one more condition, okay? Then both inclusions, so the inclusion of F into F union G and the inclusion of G in F union G, they are strongly admissible as well. And this is a very actually non-trivial theorem which we proved at the end of the first semester. So this part was the theorem of the semester for the first semester, okay? But in particular, we know that these guys are admissible, so that they induce canonical surjections for Levi-Pav algebras. And because LK, after all, is a functor, so it turns a commutative diagram, which is just the push-out diagram of a set theoretical union, of graph theoretical union. This will yield a commutative diagram. Also, here is no brainer because all these surjections are canonical, so you immediately have it. It's a commutative diagram. Okay, so I needed this first argument here to make sure that I know that these maps, which are at the bottom, exist. Okay, these maps exist by assumption and by previous reasoning. Okay, but now I want to also make sure that these maps exist at the level of Levi-Pav algebras, but they do because of this very non-trivial step. But now what really is a big deal and what really is this new theorem all about is that this commutative diagram of canonical surjections is in fact a pullback diagram in the category of algebras and algebra homomorphisms. So as desired, as wanted, as advertised, now we have a push-out to pullback theorem for Levi-Pav algebras. And the restrictions that we've got is that we are talking injective pushouts, which means just unions of graphs. And we must make sure that the intersecting of graphs is strongly admissible. Okay, I explained admissible, I explained strongly admissible in just a second. Okay, I repeat, admissibility in itself suffices for existence of the diagram and its commutativity. But in the presence of breaking vertices, which are by all means allowed here, you must have some extra conditions to make sure that you really have a pullback theorem. Okay. And also, I skipped the unitality for the time being because it's a little bit of a hassle to all the time change the categories and once considered only graphs with finitely many vertices and ones with arbitrary many vertices. But it's a very, very easy conclusion is that if F0 and G0 are finite, then all algebras in the above diagram are unital, and that's obvious because if F0 and G0 are finite, then the Levi-Pav algebras of the extended graphs are unital, and the quotient of a unital algebra is a unital algebra. So of course, all these algebras are unital. And if you look at how these maps are induced, you see that the unit is mapped into a unit. So of course, also all these canonical surjections become unital homomorphism of algebras. Okay, so now I will try to sketch for you the proof. We have plenty of time, so I will try to do it very carefully. I didn't type up the complete proof. I simply didn't have enough time to do it, but I guess it's all right because you see this proof is in a way typed at another place. It's typed at a certain publication, which I want to show to you right now. And I suppose I can now stop sharing. No, I don't need to stop sharing. I need to open a new file in my Drawboard PDF. And to this end, I will just minimize the browser and I extend, I extract the paper from my Dropbox. Where is it? Here's a Dropbox. And this is a paper which we published in the Banach Center publications ages ago. I mean, a few years ago, which proves a simpler version of this theorem. So let me explain it step by step. This is by myself. No, that's not in the other. I have to go to Reznikov. Where is Reznikov? Here she is. Okay. Okay, and here's the paper. Yeah, it was published 2020, so I exaggerated with ages 2 years ago. Okay, and let me go to this theorem. And I still didn't explain to you what is meant by strongly admissible. I will do it in just a second. Okay, but first here we have the paper. Well, the terminology here is slightly different. I don't want to waste time to reconcile it. But basically, this is a theorem which is analogous to the theorem we've got. And of course, you might complain, well, it's cheating. This is graph sister algebras. We have no idea what it is. You are talking Levi-Pav algebras. Well, no problem. Just think here that instead of a C star, you have LK. It really works very much in the same way. Okay. So here what we've got is again this assumption what I call admissible decomposition. But basically what we assume that the intersection F1 with F2 is admissible in F1, is admissible in F2. So the intersecting of sets F1 and F2 is admissible. So this gives us this map for Leavitt-Pav algebras. And then you can also prove, this was known, we proved it actually here in this paper, that this also implies that the inclusion of F1 in the union graph and the inclusion of F2 in the union graph is also admissible. So this will also yield these arrows. Here E is an abbreviation for the union. So E is F1 union F2. I should maybe write it down. Oops. But I didn't open it. Yes, sorry. I didn't open it in this Drawboard PDF. So it's wait a second. Can I? Right? No, I don't know. You see, this is why I'm using this Drawboard PDF. Okay, but it's very simple. Let me not waste too much time for technicalities. E is just F1 union F2. All right. So just by the admissibility, you know that you have such a commutative diagram, but there was an additional assumption, which was the following. There was an assumption that the inclusion of F1 intersect F2, both in F1 and F2, is actually not just admissible, it's strongly admissible. And then we also assumed that the inclusion about which we already know, the inclusion of F1 in F1 union F2 and the inclusion of F2 in F1 union F2, that it's unbroken. Okay, and we had to assume it. We didn't know that it's actually being implied. So now I have to go back to the whiteboard to explain what I'm talking about. So I will explain what I mean by strong admissibility. Okay, but first I need to remind you what the breaking vertex is. Okay, so this is a very big deal in graph algebra. We discussed it at length in the first semester, but not so much in the second semester, because breaking vertices are not really important for Leavitt-Pav algebras. I do not remember any situation in which I would bother about breaking vertices, because the idea about breaking vertices is strictly related to the idea of regular vertices. And until you start talking about the relative conpav algebras, this regularity is not important, because regularity is essential for the second Kunstkrieger relation. So unless you're talking second Kunstkrieger relation, all this idea of a regular vertex or a breaking vertex is completely irrelevant. Okay, so I have the following situation. I have some graph E, and as before, in the set E0 of all vertices, I have some subset H. So H is a subset of E0. Okay. And I call a vertex V outside of H a breaking vertex for H. You see, the concept of breaking vertex is related to a subset. We say that V is a breaking vertex for a subset in the set of all vertices. Okay, so V is a breaking vertex if it has the following property. It emits finitely many and not zero edges into H and infinitely many outside of H. So in other words, you must have a vertex which is an infinite emitter that maliciously emits non-zero but finitely many edges inside H. Okay, so then V is a breaking vertex, is a breaking vertex for H. Okay, and we say that H is unbroken in the graph E whenever there are no breaking vertices for H. I'm very proud of this terminology, you know, because everybody speaks hereditary subsets, saturated subsets, and then again you're interested in subsets, but everybody just talks the breaking vertex, but nobody says what it means that you have a subset which is unbroken. But it's just so obvious, so easy. Your subset is unbroken if it does not admit any breaking vertices. Okay. So basically, what I want to add to my list of conditions for admissibility is that this set, which is the difference set between all vertices in the ambient graph and all vertices in the subgraph, this set has to be also unbroken. Okay, so we say that an admissible inclusion is strongly admissible whenever F naught less E naught is unbroken in F. And let me explain to you the motivation of what happens here. Why is it so important? Of why we cannot ignore breaking vertices? Okay, so I have my E, which is a subgraph of F. So here's my E0, and here is my F0. Okay, and we want this set, the difference set, F naught minus E naught, to be unbroken. So it means that we disallow vertices in E0, okay, which have this property that they emit finitely and non-zero many edges outside of E0 and infinitely many inside. Okay. Why is it a problem? Well, the point is that when you look at this vertex V in E0, so that's a breaking vertex, right? If you look at this vertex V in E0, then from the point of view of F, that's an infinite emitter. Wait, I guess I somehow have it inside. I have it the other way around. Let me double check on another computer. So there's something here I don't like. Give me a second. Breaking. I might have confused the sides. Okay, checking the definition. A subset H of E0 is called unbroken. It does not exist. Yes, a vertex outside, which is a breaking vertex. Okay. And the breaking vertex is such that it emits finitely many, yes, it's an infinite emitter, which emits finitely many non-zero edges inside. Yes. So my definition of unbroken and a breaking vertex was correct. Okay. So let me look for strongly admissible. Strongly admissible. Okay, we call an admissible graph an admissible addition. Yes, F naught minus A naught is unbroken. So I did it correctly. Okay. So why am I not getting the right conclusion? Okay, F naught less E naught unbroken, it means that there is no breaking vertex for the set. So there's no vertex outside of the set, which is in E0, which is a breaking vertex. So it maps finitely many there and infinitely many here. But somehow I would like this infinity to be at a different place. You see, the idea is the following. I mean, that's something I'm making somewhere trivial mistakes. So please help me out if you can see it. The idea behind this unbroken condition is the following. If you have a vertex which is not regular in the ambient graph, then it should not be regular in the subgraph, because otherwise you are in trouble. Because if your vertex is not regular in the ambient graph, then there are no conscript relations of the second type. Remember that the conscript relations of the second type are only for regular vertices. Okay. So if by killing some vertices and some edges that end at these vertices, all of a sudden an infinite emitter becomes a finite emitter and not the sink, well, that it must satisfy the conscript relations of the second type. But they don't have any place to come from. So the thing is ill-defined, okay? So I'm now, I would like to have this infinity here, but then it doesn't, what am I doing incorrectly? This would be the situation. If I would have infinitely many edges going from E0 outside and finitely many going inside, then by killing all vertices that are outside and all edges that end at these vertices, well, I will get V, which is regular, which is exactly what I don't want. Okay, so but why is this a breaking vertex here? I'm confused. So, some things are reversed and I don't know why. Does anybody know what I'm doing wrong? Okay, let's, I mean, not okay, but I don't want to waste my time here. Let me now recall this fundamental theorem of the first semester, where we proved that the strong admissibility of the inclusions of inclusions of intersection implies the strong admissibility of inclusions into the union graph. Okay, so now I need to start sharing my screen again. Okay, and I have, no, I don't want this file. I want that one. Okay, now I will have to go back. Or maybe again, I'll just look for strongly admissible. And it will be faster. Well, everything is slow, whether you search or scroll. Okay, so page 32 is the first occurrence. Let's go there. What happened? 37. Why 37? Yes, yes, this is where I want to be. Okay. Okay, so you see theorem 1.66. Let F and G be graphs whose source and target maps agree respectively on the intersections, so that the intersecting of F and G exists. And now then, if the intersecting is admissible or strongly admissible, then respectively, so is taking the union of F and G. Okay, so that was that's the theorem, and this is a very non-trivial theorem. You see, proof is quite lengthy, and this first part, I mean, that admissible implies admissible, that was done in the published paper I showed you before. But what we were missing, this assumption that if we have this conclusion that if we are strongly admissible at the intersection, we are strongly admissible at the union. Okay, that's what we didn't know. And I think I told you something incorrect. Admissibility is good enough for inducing morphism of Leavitt-Papp algebras only when you have no breaking vertices. So when you have breaking vertices, admissibility alone might be. Wait a second. Am I saying? Now I'm confused myself, because I just showed that if I'm admissible, then I satisfy the properties of C, R, T, B, P, O, G. So no, it should admit, it should give us morphisms. So so this morphism should still exist, even if I'm just admissible. That's a little bit confusing. So yes, okay. So maybe what I tried to show you was actually wrong. Maybe it's good I didn't show it, because that's not the case. This is not what I need. All right. I take it back. I take it back. We looked that admissibility alone implies conditions of C, R, T, B, P, O, G. So it must induce a homomorphism of Leavitt path algebras. Okay, but what goes wrong? Yes, what goes wrong is things that we do to provide to have a pullback. Okay. So in the theorem I showed you in the published paper, what we assumed the strong admissibility of the intersecting of graphs, okay, and then we proved that it implies the admissibility of taking the union of graphs, but we didn't know how to prove that this admissibility is strong, so we just assumed it. So in other words, that theorem in the paper has one redundant assumption, which we now removed by this theorem 1.66. But this is a very beautiful result because, I mean, in my opinion, I maybe shouldn't say it about my own result, but I like it because it's very useful and not so obvious, not so trivial to prove. It took a while to see how it works. Not that it's such a big deal from a hindsight, but it was the most important and advanced theorem of the whole first semester. So here we go, right? That's what we use at the very beginning of our theorem, which our push-out to pullback theorem for Leavitt path algebras. That's this part. Strong admissibility implies strong admissibility. And this is interesting. It's not enough to say that if the intersection is unbroken, then if intersection is unbroken, then the union is unbroken. No, this doesn't work this way. You must really use strong admissibility to prove that things are strongly admissible, right? And that's what we do over here. I would again go back just a second to double check that I didn't screw up the definitions, but yes, strongly admissible means that the subset is unbroken. Okay, so the same subset which is correctly saturated, you also demand it to be unbroken. That's why it's so natural to define what you mean by set being unbroken. Okay, and let's go and see again what it looks like. I mean the definition. Yes. So a subset is unbroken if there does not exist a breaking vertex. A breaking vertex must be outside, and it must emit finitely many edges. Wait a second. Now I can draw. Okay. So I have my H. Sorry. I have my H in E0. Okay. And a breaking vertex for H is a vertex outside of H which has the property that it sends finitely many guys into H. Sorry, wait a second. It sends finitely many, yes, into E0 minus H. So this was my mistake. Ah, wait a second. Right, this finite set I'm talking about, okay? I'm talking about edges that end outside of H. So they're on the side where V is, okay? So I have finitely many edges going here. And because by assumption, V is an infinite emitter and has only finitely many edges ending in E0, it must have infinitely many edges ending in H. Right? So I have V outside of H. Okay, so it's here. It's an infinite emitter. but only finitely many and non-zero and outside of H. Yes, so this is a breaking vertex. Yes, and no, so I was actually correct. This is what I wanted to say. And the idea is that if all of a sudden what you want to do, you want to kill the set H of all these vertices, then of course you also must kill all edges that end in H. And then all of a sudden your vertex, which in the graph E was not regular, was an infinite emitter, after going to the subgraph, which you obtain by removing H and removing all edges which end in H, that's exactly going to this admissible subgraph, becomes regular. And here's a problem with having the relations. Okay, you must somehow your map. Well, your map exists, but it's a little bit more fancy. So. Yeah, your map exists, but you have to quotient by a little bit more. Your kernel is simply slightly bigger. Okay, so there's no contradiction. I told you that admissibility alone is enough to induce a map between Levitt-Pav algebras. So you would still have a map. However, this map will have a bigger kernel than it would have without the breaking vertex. Okay, but there's no contradiction whatsoever. Okay. So what we are simply saying is that when the set is unbroken, there are no breaking vertices, then simply the idea, which is the kernel of a surjection, has an easier description. Okay. And now what you should substitute, of course, is now. When I'm talking subgraphs, right, then my H is E0 less F0. Okay, so here's my E0, here's my F0, and this is my H. Okay, so I was right. I'm taking a vertex in E0, okay, and it must emit infinitely many edges, right? But it must have. You see here, if you look at it, that this is what you have here is F0 less F0 less E0. Well, then it's of course E0. They must have finitely many. This is why I got confused, because I have this sort of double negation, right? So saying that the inclusion is unbroken means that F0 minus E0 is unbroken, which means that there are finitely many edges emitted to F0 minus E0, but this is E0. So there are finitely many edges that start and end in E0 and infinitely many outside. So now exactly when you collapse this part outside to go to the subgraph, all of a sudden your vertex in the subgraph becomes regular, and you are in trouble because you have to generate the Kuhn-Square relations of the second type, which were not there in the ambient graph, because in the ambient graph this was an infinite emitter. Okay, so you see just such a trivial confusion because of double negation, and I got stuck for a while. So apologies for this, but I knew that if we just talk about it, we'll have it sorted out. Okay, so now you know what it means unbroken, you know what it means strongly admissible. So perhaps we can now go back to our main theorem and see how we prove it. And I suppose that to this end, I should now go back again to the paper. Yeah, but before I go to the paper, I want to use the second part of this theorem. Now, how can I go all the way down? Let me scroll it real fast. Remember this theorem from the book, where the ideal was so nicely written out for you? These are very beautiful and non-trivial theorems, but they are standard. almost there. Yep, here it is. So now I want, let me erase this part and highlight that part. So you see, whenever you have this canonical quotient map, all right, so E prime is just admissible subgraph of E, not strongly admissible, admissible. Okay, that's enough to induce a morphism. Okay, as we proved actually, independently of the theorem. Okay, so here the whole thesis that I mean, in addition to what we already used, that this quotient by a graded ideal must be a Leavitt-Path algebra of an appropriate subgraph in itself. That's highly non-trivial in itself. But now we are looking, well, what is the ideal, right? We have a map from LKE to LKE prime, where E prime is an admissible subgraph in E. And what is it that we have here? Well, first, we take all idempotents that are generated by vertices that we remove. It makes sense because we are killing vertices which are outside of E prime. So we are setting them to 0. So they should be generators of our ideal. And if the inclusion is unbroken, then that's it. Okay? Because if the inclusion is unbroken, then there are no breaking vertices for this E0 less E prime 0. There are no vertices outside of E prime with this property that they are breaking vertices for E0 less E0, E prime 0. Okay, that's what unbroken means. Okay, but if W is a breaking vertex for this E0 less E0, E prime 0, then of course it must be outside of this set, which means it must be inside E prime 0, okay? And in E prime 0, it is regular. That's what we are just talking about, right? E prime 0, it is regular. Because it emits non-zero and finitely many edges, which ends in E prime. And now we can form the following projections. Remember, this is very much like these QWs that we were doing for relative compact algebras. So we take such a vertex W, which is regular in E prime. And of course, we want it to satisfy the second Kunstkrieger relation, right? I mean, it must satisfy the second Kunstkrieger relation in LKE prime. But now it doesn't follow from any relations in LKE, so we have to force it. So we have to just add additional generators to our ideal. So the map is still induced, there's no contradiction, but now the kernel is bigger. You see, in case when the set is unbroken, it means that there are no breaking vertices for this set. There are no breaking vertices when this set is empty. And you're generating ideal just, the ideal generated just by this idempotence chi W, where W is outside of E prime, okay? And now these guys are also idempotents, can be very easily verified. And these idempotents, well, they have to die when you go to the quotient. But of course, this is highly non-trivial to prove that indeed this is all you've got. That's really your kernel. And I wanted to emphasize why it is so important. It's important in proving our theorem. So when we assume strong admissibility, we assume that these sets are unbroken. Okay, we assume that the inclusion of the intersection in both graphs is unbroken. Okay. So for this inclusion to be unbroken, it means that your graph minus the intersection is unbroken. So there is no breaking vertex in the intersection, blah blah blah, and so on and so forth. And basically you see that your ideal, the kernel of the surjection is generated just by these projections that you remove. And then it's much easier to prove a pullback theorem when the description of this idea is like this. So that's exactly why we needed it, okay? And we needed it at all levels. We needed it for the kernels of all these surjections. So we are unbroken by assumption at the level of the intersection, and we are unbroken by conclusion at the level of the union by this nice theorem from the first semester. Okay, so that's where this textbook theorem 2.54 is so useful in the proof of our main theorem of the whole lecture course. Okay, but now let me go back to sharing my paper. Oh, I closed it, so let me open it again. Okay. And see how the proof goes. So for starters, ignore C star. We can equally well talk Levitt-Pav algebras. You see at the end of the proof there is a remark saying, see, maybe I can highlight it. How do I do it? Nope. Yeah, like this. Okay. So please pay attention to this text, that one can also prove theorem 3.1 in the setting of Levitt-Pav algebras. And the Levitt version of theorem 3.1 is completely analogous due to certain corollary from the Levitt-Pav book, which I will explain in a second. This is something very important. So if you now look at the proof, so first use a theorem which I think Oskar Stachowiak proved in exercise session, maybe even already in first semester, I don't remember. You see, there is a very famous lemma, if you want, that tells you when a commutative diagram of algebras, actually of abelian groups, is a pullback diagram. There are like three conditions, which were nicely written down by Pedersen. But I don't think I'm pretty certain he was not proving an original theorem, but it's nice to cite him because we have it so explicitly, okay? Okay, but these conditions of Pedersen for a commutative diagram to be a pullback diagram simplify quite a lot when all the maps that you're talking about are surjective. One condition is tautologically fulfilled. And basically, the only thing that you have to prove is these two conditions. Why I cannot, how to highlight it? Either it's too much or it's too little, it's so frustrating. Okay, so this is one condition and this is another condition. I repeat, this is under the assumption that these maps, chi1 and chi2, are surjective. Then it's automatically implied that the induced maps in the diagram, pi1 and pi2, are also surjective. That's a little standard lemma, I guess, already in category theory. Okay, so these are the only two conditions that we have to check. And if you look at the proof, we are not really looking at kernels of sister algebras. We are looking at the algebraic backbones, which are in fact the kernels of maps at the level of Levit-Pav algebras. Remember that I know we haven't formally defined it, but just remember that the graph sister algebra is nothing but the universal enveloping sister algebra of the Levit-Pav algebra, where your ground field is complex numbers and your start structure is natural given by the assigning to edges ghost edges. Okay, so and there are some beautiful non-trivial properties. You see, in general, the universal enveloping sister algebra of the star algebra it doesn't have this initial star algebra as a subset in itself. It's a subset quotient in general. But for Levit-Pav algebras, we can prove that the Levit-Pav algebra is actually a subset, a subalgebra of the graph sister algebra, which it defines. Okay, so basically, then if you look at these proofs, well, you have to prove these two conditions. One is that the intersection of kernels is equal to 0, and that is quite a tough cookie, but they use a very, very beautiful property of ideals in a sister algebra. Okay, that is the intersection of sister ideals, so they must be closed ideals. But the intersection of sister ideals is equal to their multiplication. And mind you that this is absolute nonsense in pure algebra. If you take some polynomial, so for instance, in particular, you have that I squared is equal to I for sister algebras. For an ideal I in the sister algebra, its square is equal to itself. Okay. But if you think, for instance, say about the polynomial algebra generated by one generator X, then if you take the ideal generated by X, then it's not the same as the square of this ideal, because the square of the ideal is obviously the ideal generated by X squared. And these ideals are not equal, because X is in the ideal I, it's not in the ideal I squared. So in general, it's completely false that the intersection of ideals is equal to the multiplication of ideals. But it is true for sister algebras. Now, this important corollary that is cited here at the remark, you know, this corollary 2.511. It says something remarkable about graded ideals in Levit-Pav algebras. So I just showed you a counterexample. In general, in algebras, it's just wrong. It's the difference between, say, polynomial functions and continuous functions. For continuous functions, no problem, because you can always find the square root. Okay. So that's why I squared is equal to I. Obviously, I squared is inside I. Why is I in I squared? Well, because when you are talking continuous functions, just roughly speaking, so the heuristics, you can take the square root. So anything is equal to the square of its square root. So everything in I is in I squared. So roughly speaking, okay, but of course it's not as trivial. But this corollary 2.511, which is cited here from the Levit-Pav algebra book, it says that if you take graded ideals in a Levit-Pav algebra, then the intersection equals to their multiplication. Okay, and this is a remarkable property, because now, of course, because we are talking about maps induced by graph homomorphisms, of course, the grading is preserved, so the kernels are graded ideals. So this intersection of kernel is actually the multiplication of kernel because they are graded ideals. Okay, so we can use the same magic as we are using for graph sister algebras. And now you can see that what basically what we are using here, we are using this simpler expression for this ideal for the kernel. Okay, we have a description. Yeah, there is one thing which I skipped, but basically you can prove that if you take the ideal generated by vertex projections, then in fact this is nothing but the linear span, and now we are taking all paths that end at this vertex and you construct the following element. So alpha is a path which ends at your vertex, and beta is your path that ends at your vertex. So when you have alpha beta star, then this is a path, because the end of alpha is equal to the beginning of beta star, which is the end of beta. Okay, so take the linear spans for all such paths. You take all paths that end in your vertex V, and then you invert one of the paths by starring it. And then the linear span of all such paths is exactly the ideal generated by vertex projections. Okay, and knowing that, due to this assumption of strong admissibility, due to this assumption that our inclusion is unbroken, we don't have these other idempotents which do not come from vertex idempotents. They come from more complicated idempotents. Then we can have a much simpler description of this ideal. And this is exactly what we are using here. This is exactly what we are using here. And we are combining it with this remarkable property 3.3. Yeah. And it's much easier to determine what is the multiplication of these two ideals. Because if I have one ideal as a linear span and another ideal as a linear span, then of course their multiplication will be the linear span of all guys multiplied together. And now I just look at what I multiply, and I realize that what I multiply, no matter what element of my linear span I take, okay, of course it's enough to look at generators, because the linear span of multiplication, the multiplication of linear spans will be the linear span of multiplied elements that span. So take these two families, you multiply them out, and you see what you have as a combination. And then you realize that by the very condition that you have on your graph, that these guys always multiply to 0. Okay, so if these generators that span the subspaces multiply to 0, then of course these linear spans multiply to 0. So multiplication of ideals is equal to 0. So the intersection of these is equal to 0, and the first Petersen condition is verified. Okay. And now when you look at the second condition, again, you use the fact that you have a very good description of what your kernel is. So that's a little calculation, but it's not a big deal. Right? Basically the way you prove it, you check it at the algebraic level. You see this inclusion that I have over here, this one. This inclusion is exactly the inclusion that you have for Leavitt-Pav algebras. Only later on I say, aha, so by the continuity of pi2, I can now close these ideals with a C star norm, and I can see that indeed this means that the kernel of chi2, which is the closure of this ideal, is equal to pi2 of the closure of this ideal, okay, using the continuity of the star homomorphism. But that's redundant. If we are talking Leavitt, we already done when we had this highlighted part, because these are this is the kernel of chi2 at the level of Leavitt, and this is the kernel of what was the other one, pi1, whatever, of the other map of pi1. Yes, the kernel of pi1 at the level of Leavitt, and that's it. The condition is satisfied. You don't have to argue by continuity. So you see, by having this corollary, this highly non-trivial corollary from the Leavitt-Pav book, that the intersection of graded ideals in Leavitt-Pav algebras is the same as multiplication. Without it, you cannot do anything. Okay, I mean, I don't know how to prove it. You can basically follow this proof verbatim and have this theorem proven for Leavitt-Pav algebras. And I will see that this one assumption with having this theorem is redundant, because by this theorem from the end of the first semester, we know that strong admissibility of the intersecting of sets of graphs implies strong admissibility of taking the union of graphs. So we don't have to have this extra unbroken assumption that is put in here. So this proves the theorem. Okay, this proves the theorem of the semester and of the whole lecture course. And to end with, I would like to tell you a little bit more about state of the art. because this theorem is beautiful and okay, maybe I shouldn't say beautiful by theorem, but I proved, but I'm really happy with this result. It has, I believe, a much better version, but we haven't finished proving it yet. You see, you can do without this strong admissibility, but you must assume something of a distribution of regular vertices. And somehow it is not unlike this one color condition, okay? But I didn't have time to figure it out. This theorem is still a conjecture, but let me spell it out using the whiteboard. So you see, that picture was after all correct. I just got myself confused. So let me write it as a conjecture, and that's something that we really hope to finish proving very soon. I mean, I bet any money you want that this is true, but that is until you finish your proof, you cannot claim the theorem. Okay, so let the intersecting of F and G be admissible. Assume also, let me call it the regularity condition. Well, I'm using, we have so many regularity conditions that's somehow annoying, but it really is about what happens, how do you relate regular vertices in, sorry, F. Sorry, I should write it like this. If you take regular vertices in the intersection graph, it's somehow, I don't remember, I'm making it up. Somehow it should be equal, I don't know, to the intersection of regular vertices, stuff like this. And remember that this is very subtle, because when you go to the intersection graph, I mean, you are really limiting edges that are emitted. You can only talk about edges that are in both graphs. So that's, this is a condition of that sort, okay? And and when you throw in this condition in addition to admissibility, then it's something definitely more general than strong admissibility. I mean, you don't need to assume that your set is unbroken, okay? So in particular, when you look at this ideal, you must also consider the other idempotents you do admit breaking vertices, okay? So you must look at these idempotents which are chi v, sorry, chi w, minus sum over all E running the preimage of W, and here chi E, chi E star. And now what we are talking about, say, the inclusion of Fg in F. So to have a breaking vertex for this inclusion, it means to have a vertex in this intersection. So, okay, so here it should be the intersection map, okay? So I have a vertex W in the intersection, which is an infinite emitter in my graph F, but it is a regular vertex in the intersection. And therefore, this makes sense. I'm taking here the preimage under S cap, all right? So this is a finite sum. And well, you can check, but this is not important. That's very easy. We did this stuff with QW, but the same thing. There is nothing new. And these guys are additional generator of your kernel. So now this means that when you look at this kernel ideal, it will be a more complicated linear span. In addition to these paths that I will describe for you, you have some other paths with a slightly more complicated description, but actually you can easily figure it out. Now basically what you're talking about, if you want to admit these idempotents as generators of your ideal, and now you want to write this ideal as not in terms of just generators, but in terms of a linear basis, not a basis, as a linear span of some family of elements, then you have to add to this family, which I'll describe to you, the following family. You take all paths that end at W, say alpha and beta end at W, and then what you do, you take chi of this path here, say chi alpha, and here take chi beta star, and you multiply it. And these are your elements, okay? You see that it makes sense because alpha ends in W, right? So it also makes sense because beta star begins at W, okay? And how about here? Chi E starts at W, so chi alpha, chi E is also non-zero. And when you look at chi E star, chi beta star, well, that's the end of E star must be the beginning of B star, but it means that the beginning of E must be the same as the end of beta, but the end of beta is W by assumption, and the beginning of E is W by assumption. So everything works. It's something which is not zero. So you take all paths alpha, beta that end at W, and you take the linear span of elements of that form. So now when you do a calculation in order to prove that the multiplication of two ideals is equal to zero, well, you have a much more complicated formula. Instead of having just one case, you have four cases, because you multiply elements from the first family, you multiply elements from the second family, and then you have cross terms, first family times second family, and second family times first family. So you have to consider all these four cases and still prove that it multiplies to zero. And this I checked. This definitely works. What I didn't have time to check was the other condition, okay? Well, now again, the description of ideal is more complicated because of this additional family that gives you your ideal as a linear span, but I bet any amount of money that it works. And then when you check these two conditions, well, you're home and dry. You know that this is a pullback, okay? But in order to check, and I'm not sure if it's in order to check this condition or the second one, probably this condition. I realized when trying to prove this condition that it wouldn't work with just admissibility, okay? But at a certain moment, you have to know something about the distribution of regular vertices, something of that sort. I'm not sure, I'm not telling you that this is this condition, but something like this, okay? And when you when you have it, then this condition checks out, and presumably that so does the second. And I just vaguely remember that it's somehow related to this one color condition, but it's been so many months ago when we looked at it that I don't remember it right now. And it still would take, say, much more than just a few hours to prove it. So I gave up, and I decided to show for you a theorem I'm certain of with strong admissibility assumptions. And here I put it as a conjecture, but you can place your bets on it. This conjecture is definitely true. I mean, okay, I can't say definitely true until I prove it, but I find it extremely unlikely that it would not work. And let me give you one more state-of-the-art comment, which is much more fancy. So I discussed it with Andreas on Friday, I believe, after the seminar. Okay, even if we solve this, answer this big question, when we find some far less restrictive conditions than, say, admissibility and so on and so forth, that we go beyond the unions of graphs. Of course, that's a very important case, and we have zillions of examples where this theorem is applicable. It really fits beautifully in non-commutative topology. The very simple example is if you are gluing two quantum disks into the generic Polish quantum sphere, then that's this is your Teplitz algebra graph, and this is your circle algebra graph, and you take the union of these graphs. So you see the intersection of these two graphs is the circle. So then the union is, of course, this. That's a union graph. You have injections everywhere. Okay. And you can check that this is admissible. Of course, it's even stronger admissible because this graph is finite. So there's no problem with infinite emitters and breaking vertices. Okay. And now you have the induced pullback of sister algebras. So this is the equatorial Polish quantum sphere. This is the Teplitz algebras of functions on the quantum disk. And here's the symbol map going into continuous functions of the circle. Okay. So this is how you glue two quantum disks over the boundary circle into a two-sphere. And there's zillions of far more complicated examples using, you know, balls, projective spaces, whatnots. I mean, it's you can really give lots of interesting and natural examples. However, if you go to if you look at non-commutative topology, you immediately go beyond this setup. You immediately realize that just the union of graphs doesn't make your day. Okay, here this example of a sphere was, you know, classically this would be this push out. You have classical disk, you have a classical disk, you glue it over the boundary circle, and then you get it to sphere, right? So that's the classical push out. And funny enough, you can do the same with graphs. But now look at spheres. You can also do the following. You can take your disk, you can look at its boundary, and then you can shrink the boundary to a point. And what happens when you shrink the boundary of a disk to a point? Well, you also get a sphere, right? Only now this point will be the pole. The circle will be mapped into the pole. Okay. So these maps are injective, but these two maps are not. And again, that's something which is again happening at the level of graph sister algebras. So you can again take the Teplitz algebra, which you think about as continuous function quantum disk. You have a simple map into C of S1. Well, and here you can take evaluation map. This gets you into complex numbers. Okay, you take the pullback of these two star homomorphisms, and guess what? You get precisely the sister algebra of the standard Polish sphere. But in terms of graphs, what you have is the following. Here you have your circle, here you have your Teplitz graph, here you have the point, and here you have countably infinitely many edges between two different vertices. Okay? So something funny is happening. I mean, you include these vertices, this one, so V and V. Okay? Here, obviously, you include this circle as part of the Teplitz graph. Okay, so here's inclusion, here's exclusion. But now something funny happens. In order to somehow complete it to what you'd like to be a push-out diagram, well, you have maps which are not inclusions. You collapse certain things. And in fact, you collapse it to a very funny way. I mean, here it's a no-brainer. You have a circle and you collapse it to a point. That's just a constant map. But here, that's something a little bit more weird. What you are doing is you are mapping this edge, say, to the first edge here, then going around the circle, and then by the edge you map to the second edge, and so on and so forth. So we also here have countably many paths from this vertex to that vertex. So V, W, V, W, okay? But here's a certain problem, because somehow, you know, what happens with all paths which start and begin at V? Always looping around, okay? That gets completely killed. It gets collapsed, right? But it turns out actually, and this is what is absolutely amazing, is that it is more convenient. You see, when you look at these maps, I mean, they are concrete maps, okay? Oh, what have I done here? Of course, that goes in the wrong direction. Why nobody shouted? Of course, just this is the unit map, okay? What turns out is quite convenient is to reverse here the direction of these arrows. So you get something truly ridiculous. When we look at these two parallel arrows, they are honest, admissible, or strongly admissible inclusions of graphs, okay? So they contravariantly induce these maps. So these maps are induced contravariantly. But now here, all of a sudden, we recall that we also have this covariant factoriality. And we say the following, okay, I want to have a path homomorphism of graphs, not graph homomorphism, but path homomorphism of graphs. And I map my first edge to this edge. I map my second edge to the path, which is go around the circle and go out, and so on and so forth up to infinity, okay? And of course, I'm identity on vertices. It turns out that this is a very good, very honest and decent path homomorphism of graphs. And it easily satisfies our functoriality assumptions so that it can covariantly induce these maps. Okay, so these two maps are induced covariantly. And these two maps are induced contravariantly. And yet, this is a pullback diagram. So I admit that it is something truly tantalizing, flabbergasting. It's a very weird situation in which I have a diagram with a property. I have a diagram, and to this diagram, to two arrows, I apply contravariant functor. To the other two morphisms, I apply covariant functor, and I end up with a pullback square. This is really puzzling. So I don't know how to characterize a commutative diagram, a certain diagram in a category. Would it have this property? How to characterize it abstractly, not by an example. But it has this property that if I apply one covariant functor to two parallel morphisms and another contravariant functor to one parallel pair of morphisms and another covariant functor to the other parallel pair of morphisms, but I get a pullback. How to sort it out? And I'm not talking even in the context of abstract categories. Just let's do it for path algebras, for graphs and Leavitt path algebras. That's a bit weird. So what we did. We generalize the situation to a big extent, but roughly speaking, the whole idea is that when you have loops here, basically what you do, you can collapse them to their base vertices at the expense of creating countably many edges. So roughly speaking, that's a philosophy. You can have very general graphs which satisfy this property. We we did write it down, and it's not just this example. This was the motivating example, but now we have much more complicated example. This is a very general theorem, but still, despite its big generality, well, it has this limitation. This is a certain particular, construction here. Assume that this graph has no loops somewhere there, and here you assume that all paths are pointed, and so on and so forth, and which means that no path ends in a loop. If path ends in a loop, then somehow that's something that you ignore. It's complicated. I mean, you can go to a very high level of generality. I don't remember. We have it nicely written down, but somehow it's still very constructive. It's not conceptual. Okay. What we did was took this lemon of an example and we squeezed all the juice out of it. All right. But what if it's not a lemon? What if it's an apple? I want a theorem for all fruits, not just for lemons. And this is frustrating. I don't know how to abstractly characterize such situations so that at the end of the day we have a pullback diagram. Okay. And even though here in this theorem we use the covariant factoriality, and then we have this funny situation that we apply simultaneously to one diagram, both covariant and the contravariant functor, we can try to reverse it somehow. We try to manipulate and somehow say, okay, but this morphism here is actually injective. So if you somehow ignore this path, which is these paths which are killed, which are not in the image, then you have a bijection between paths. So we can reverse, and then this reversed thing you can somehow axiomatize. But here you run to a certain problem. I mean, this is a problem of a domain, right? You can say, oh, that's fine. This is now induced contravariantly because I inverted the morphism to which I applied the covariant functor. But now, what are these formula? What happens? How do I write it down? Is it really the same as this contravariant functor that we always use? When what we do, we use the injectivity here. We invert the map on the domain. I mean, on the image. We invert it on the image and then take the contravariant construction respect to this one. Does it agree with what we have here? Because at the end of the day, it must be just the covariant construction with respect to the arrow which was not inverted. Okay, so I hope it's clear what I'm saying. We have a map F here, but then we have to use the covariant construction. So what we do, we somehow invert this map, and it goes into the opposite direction, and then we somehow try to take the contravariant. But is it really the same as F star? I'm not sure. Okay. And also, that's easy to write, but you have to make sense out of it, because it's defined just on the image of F, not on the whole graph. But it is a very, very useful theorem, which is, for instance, very much needed in proving that we have a CW complex structure in quantum complex projective spaces. And you see, when you're looking at, and actually this case here, this is like CP1Q, and this is CP10, but it works in any dimension. Basically, what I can upgrade this diagram to is the following. I can have CPQN, a quantum complex projective space. I can have CPn-1Q. Okay, so no problem. We have surjection of sister algebras here. But now here I have a defining Waxman-Soberman quantum sphere, so it's S2n-1Q. And now this is injective, right? Because this is the fixed point sister subalgebra by the U1 action on this sister algebra. Now here I have surjection because it's the bounded ball. So here I take the Holm-Szymański quantum ball. And here I have a certain funny map, which is a bit difficult to describe even classically. And then this is a pullback diagram, okay? And we prove that this is a pullback diagram using precisely our theory. So as you can imagine now when I draw here these graphs, they are far more complicated. These are very complicated graphs, but they do satisfy the assumptions of our theory. And therefore, by our theorem, we know that this is a pullback of C-star algebras. And this way, we have this CW complex structure for the quantum complex projective space. Okay, so that's not just shrinking circles. I mean, you can be a little bit more general. Okay? It's here you are not shrinking a circle. What you are doing over there had a quantum disk, and you shrink the boundary sphere, which is the circle to a point. Okay, but in general, what you do, you take the boundary sphere of your ball, and you shrink it, you quotient it to the complex projective space. Right, the ball is even, so the boundary sphere is odd. So dividing that's the Hopf vibration, dividing this odd sphere by the U1 action lands you exactly on the complex projective space. So this is this kind of funny surgery that you do, right? You shrink the boundary sphere, you quotient it to the projective space, and this is the push-out structure, and then this is a push-out diagram for the CPN of a higher dimension. This is simply saying how to produce higher dimensional projective space by attaching to the lower dimensions to the lower dimensional projective space a higher dimensional cell. See, this is n-1 dimensional, and I attach something of complex dimension n, not n-1, in an appropriate way. And this is how I obtain my CPN. And what we showed is that it works just as well when you quantize, when you go to the non-commutative setting, when they get non-commutative deformation. And this is where this theorem becomes so useful. So that's the state of the art. Yeah, there are some further extensions. It's by no means everything that is proven, but I suppose that's enough. I think that I told you as much about push-out to pullback theorem as you want to know for the time being. And I thank you very much for your patience and attending the class for the whole semester. Now let's make a half-an-hour break and resume at 5:15. And then we'll have the final half an hour of a recitation class. And if Majid will finally make it, he will explain his faithful flatness. For the time being, let me stop recording and see you in half an hour at the recitation. Oh, hello, Majid, you are here. Perfect. So let's, I need a half an hour break. Let's have half an hour break and resume in half an hour. Okay, I stop recording.